Okay, so remember we've been looking at the unit circle, we've been looking at the different parts within the unit circle, how cosine, tangent, sine relate. And we've been looking at the fact that within the 4 quadrants there's positive, negative, and so forth for each value, and then we look at point P. If we look at the value of point P within different spots, then that's how we're looking at, right, this point P, we're looking at, that's how we start drawing our graph, which is nice and curved. So our graph only comes from one of our sine, cosine, or tangent. So it's important to note that, of course, in this area, the first quadrant, this is where, you know, all are positive. So I got my A, yeah? And then you go, this is my second quadrant. In this one, of course, only sine, right, is positive. And then I look here, this is my third quadrant. T is only positive. And then in my fourth quadrant, I've got cosine, right? All science teachers cheat. Just to get us started, okay? So let's start by looking at the sine graph. The sine graph, of course, going in the first quadrant, positive, second, positive, third, negative, fourth, negative. So if we're looking at plotting it, we're going to plot theta, whatever our value is for the angle, with the x-axis along the bottom, and then my y-axis will be my sine. So that's my, you know, my value of 1 or negative 1, anywhere between that value. So we can draw it. We've got to look like this, all the way across. Of course, there's my y. Here is my x, but x, of course, is going to be theta, and this, of course, is going to be 1 and minus 1. This will be my sine. And then I have my values across. 180 in the middle, 360 at the end. And we know that in the first 2 quadrants, of course, it's positive, so it always starts at 0. We know that that's, you know, from what we've been looking at in our exact values. Of course, at 90 it's 1, so that's going to give me another point. At 180 it's going to be back down here. Change the colours so that we can see. And then we go negative, so down the bottom, if this is 270, and of course this comes down here and back up to 0 again. So we've got now one nice part of our graph. Now, of course, mine's not perfect, but you get the idea, and you can see obviously that it's difficult to draw it on the iPad. You can also go back through and look at the values related with our pi, because remember we've been converting to radians. So if I looked at 90, of course this is pi on 2, 180, I've got pi at 270, 3 pi on 2, and of course at 360, this is 2 pi, right? And of course you should have your nice curve as you're going through your graph. So if I redraw this with a bit more care, we can see that my graph's a little bit better, right? As long as you scale out your x-axis accurately and scale out your y-axis accurately, so that along here you've got this amount is the same as this amount, and we break it up into 4 sections that are even. Of course, mine's not perfect, but you will have graph paper. Then you can see that the graph's going to be nice and curved and go all the way through, and you'll get this nice same distance here as here. It's important to remember that this is called the amplitude. So our amplitude for the sine graph is 1, and this is the period. So the period for a normal sine graph is 360. We can change the period depending on how our equation is written. So this is where you start with your original graph. Just like when we're looking at quadratics, we look at our original graph and then how it gets changed according to other variables. So that's what we're going to start looking at when we look at solving and other factors that we can use to change the graph. And remember that all of these points come from the y-coordinate of point P when we're looking at our unit circle that we ran on our first slide. So that would point there. So just to recap, we found our points by looking at the y-coordinate of point P on the unit circle. So that's our sine theta, and that goes on our y-axis. So this one on the side. The amplitude for this graph is 1. That's how much it goes. It's displaced from the x-axis, so it goes above the x-axis or below it, and the period was 360 or 2 pi. That was how long it took to go through one rotation. So we can do exactly the same thing with the cos graph. If we reflect on our unit circle again, we know that the x-coordinate of point P on our unit circle is, of course, the cos theta value. So we can go on the side here, we're going to plot that point. So this actually becomes our y equals cos of theta. Now that is not to be confused with the y coordinate of P. It is the x coordinate of P on that unit circle graph. And then along the plot on our x-axis, that's going to be our theta, our angles. So we can still go across. We'll always spread it out nice and evenly. And of course have -1 and 1, right? And when we plot it, the difference here is that when we plot the cos graph, when it's at 0, we know that cos, the x value, is 1. So we're going to start at the top. And then we will go through 90, that's where it's 0. At 180, it's going to be negative. This is straight from our quadrants. 270. And 360 goes back up to 1. And then when we create our curve, we'll be a bit more careful this time. Right? We go through nicely, and we will have one period, right? So that's one cycle again. So if we're looking at this graph, we can say that the amplitude is 1 again. The period is 360 again, and we know that that's one cycle. So we could change that depending on what the equation was or the multiples in front of our cos and those sorts of things. Like when we're looking at quadratics again and how that translates or changes the graph, we can do the same things with a sine and cosine graph. Now we just recap the definitions of amplitude and period. The thing about amplitude is it's from the line of reference. So if you're looking at a graph, an example, and it said something like, you know, it's high tide's at 2 meters, but it's always starting, you know, it never goes below a certain level. You have to look at where the level of reference is that it's starting to. So it won't always be the x-axis. So also the period of the graph is the time taken to complete one cycle. So the time taken to complete one cycle might not be 360 degrees. We won't always have angle and sine on the side. We can use the sine and cosine graph to replicate other real life scenarios, so things like wave tides and then other sorts of things like that, especially used in science and physics. We compare the unit circle to the graph, then we can see how we get our reference angle. So if I was looking at this, I can see that of course this value corresponds to this value because they both form the same bit from my y, which is my sine. But then if I look at the graph, I've got my nice curved bit here. Well, 40 and 140 falls in that first bit. Now of course this is a parabola, this portion, so if I'm looking at that parabola, then I can see that they're going to meet the same value. I'm going to have two values, right? So that's going to equal the same value on the y-axis, which is why we get the same value for both. Same thing if I'm looking at two larger values where sine is negative. I can go back down and say, hang on, that reference is the same, which is why we end up with the same reference, right? So it's all part of looking back at those reference angles. So it's all kind of coming together now. Now that you've worked through this, have a look at the graphs of trig functions worksheet, not the one where you draw the graphs, but the one where you answer the questions, because that explains really nicely how we can see the different reference angles, especially in the 3 examples on the first page which have been provided for you, and then you can start to look at the questions on the following page.